Did I tell you about the second time I videotaped ever? I had a water bottle sitting in front of it, so it was like an Escher thing. Wow, it's really strange. I say, oops. Okay. You can stay there. Earthquake. All right, so real quick, this is what I was desperately attempting to recreate. That's too bright. So the first part of this, we did some of this last time. You guys with me? So go ahead. Let me see. Let's do a little review. Try to go ahead and do these two. Summarize these and try to do these first two problems. Tossing coin. Want to know probability exactly 9 heads, exactly 2 heads. So just take a minute and figure this out. Alright, so how are we doing? I'm hoping, got the sense that most of us are okay with this equation, this formula. If I can trust you guys, I don't know, sometimes you don't tell me. So this would be set up, I got 14 flips, I want to choose 9 of them to be heads. So it'd be 0.5 to the 14. I like it. 0.5 to the 9, 0.5 to the 5, which would be just 0.5 to the 14. Kick ass. And then to put that in the calculator, show off the calculator. Alright, so it would be 14. Ruh-roh. Give you one of these?
Yeah. Thank you.
14, how do I get to choose? So math. Probability. Number 3, choose. So 14, choose 9. And if you have the newer one, you have to actually hit the over arrow to get out of like an exponent or a subscript or something. Time, and then 0.5 to the, is everybody cool with this? Did I hit times? Good job, Jeff. Times 0.5 to the 14. Is that cool? Argument. Well, this is good. All right, I'm glad I didn't make a mistake. If you ever get like a syntax error and it gives you the go-to option, choose the go-to option. Oh, so it's freaking out because what did I do wrong here? Let's see.
Forgot to delete that extra exponent spot.
All right, there you go, calculator. Okay. Did you guys get that one?
Yeah.
What's up? Here we are. So 0.1222 basically. So this one would be the same way. 14 choose 2 times 0.5 to the 14. Now officially, what would it be? It'd be 0.5 to the 2nd power times 0.5 to the 12th power. But that's freaking 0.5 to the 14th power, right? The one time you can combine those is when they're both 0.5. I like it. So again, it'd be 14, math, probability, choose 2 times 0.5 to the 14. So I get 0.0056 basically. Okay, so we did some of that last time. If you compare that now, so what I did here now, this is a lot easier to see obviously down here. Just I want to bypass this for a second. If you look down here, there's the histogram. There's the table of values. So if you did the formula for every one of these, so we just did the one for 2. If I round it 3 places, is 0.006. The one for 9, if I round it 3 places, is 0.122. Is that cool? Yes, ma'am.
How do you copy the line before?
Oh, if you have the newer calculator, you just have to hit the up arrow, and then you hit enter, and it copies it for you. If you have the older one, where there's a bunch of parentheses and stuff, then you have to hit second enter, and it just puts the last thing. If you hit second enter again, it puts the next to last thing on there. Does that make sense?
Yep.
So forth. Yeah. So if you have the older one, just hit second enter, and it pulls up the line. If you hit second enter again, it rewrites that with what was before that. Hit second enter again, it's whatever was before that. And I think it goes back like 8 places before it goes. My memory held. I think. I can't remember. More than that? Okay. All right. Cool. So let's come back to here. Well, I think we did this one last time also. The mean, of course, would be what? Out of 14 flips, I expect how many heads? 7. Because it'd be 14 times 0.5 would be 7. And if you look at the picture, the highest bar is 7. So the mean should be close to, if not the highest bar. Woohoo! The variance would be 14 times 0.5 times 0.5. 3.5. I like it. I gave so much space there. And then the standard, how do I get the standard deviation then?
Take the square root.
Take the square root. What's that?
1.871.
Alright, I like it. Cool. So that's old news also, right? So we got those beautiful formulas for the mean and standard, the best formulas we've seen yet. So the point I try to make, hopefully I made this point last time, but I really try to make this point because it's all about the area. If I draw my probability situation so that the total area is 1, then the probability for any section of that will equal the area of that section. You guys with me? A little bit? No? So, if I said the area, alright, so let's pretend like the area is 1 square foot, right? So it's 1. And I have a section that is 1/4 of a square foot. And I just start throwing stuff at it. I don't count anything that falls out here. I just start throwing stuff at it, just throwing stuff at it. What percentage of the stuff should hit here? 1/4 of the stuff. Doesn't that make sense? I mean, why is it so likely that something falling from space will land in the ocean? Because over 2/3 of the Earth's surface is ocean, right? So there's a higher chance that it's going to hit there because there's a larger percentage that's that. So the area equals the probability if the total area is 1. Because then you're talking about if you have a part that is 25% of the total area, what's the chance that a randomly thrown thing is going to hit there? 25% chance. I like it. So I'm trying to make this transition. We did the uniform probability. I don't know why I didn't print out too well, but that's just a picture of a box. Ooh. We did the uniform probability. So if I do set up, and what would the uniform in that mean? What's that? What's that mean? The uniform is dressed up like a mailman. What's that mean? What's that word mean? Uniform. Spread evenly. I like it. So nobody's higher than anybody else. So if I had a uniform distribution from, let's say, 5 to 9, and I know it's uniform, so I know it has to look like this. Let me stop there. I know it does, because it's got to be uniformly distributed to every number from 5 to 9. That's what it means. If somebody says, I have a uniform distribution from 5 to 9, I can draw that. To force the area, the total area to be 1, what height do I pick? How do I make the area that 1? Well, how wide is this? 4 times what is 1? 4 times 1 is 4. 4 times what is 1? 1/4. What's the area of this now? The length is 4. The width is 1/4. The area, the probability, the area is 1.
Yeah.
Right? So my probability is 100% is represented by this picture. So if I can draw the distribution as described and force the area to be 1, then if I ask you questions like, well, what's the probability it's from 6 to 8? What's the probability I get something from 6 to 8? Well, it's just the area of that thing. What's the area of that thing? That's what that will look like. The question will look like this. Yeah, so it's going to be a width of 2 times a height of 1/4. So it's a 1/2 chance that I'll get there. I like it. I like it, maybe. So try to transition from this and the idea of areas, because each rectangle is an area equal to its probability. So area is probability. To here, area is probability, as long as the total area, the whole thing is 1. I like it. So then we're trying to make probability questions easier to answer by forcing them to be like a geometric problem. Those are easy, unless I have a gross shape, right? I like it. So you're like, triangles, no problem. Trapezoids, oh shit, a trapezoid. The harder you get, you're like, oh, what was the formula for that? Oh shit. You kind of with me a little bit? So you could have a trapezoidal. We won't. Don't freak out. You could have a triangular one. I talked about that last time. If you go further in probability, take higher level probability, you'll start talking about all kinds of freaky distributions. All right. So with that in mind, that it's all about the area to figure out the probability. Let's transition into chapter 6. So chapter 6, we actually come back to talking about normal distributions. So the problem with a normal distribution, this area will be 1. The total area is 1. But the problem is, if I want to know the probability from here to here, what shape is that? It's not a rectangle. It's not a trapezoid even. Because 3 sides are nice and straight, and the last side's all freaky. Oh, scheisse. I could estimate it, but we're not going to. What we're going to do, we're not going to do, if anybody, again, a few of you guys have taken calculus. So one thing that calculus does, and I know when I say that word, you guys are like, yeah. But one thing that calculus does is it just gives us a way to calculate the area under any freaky shape. So we let the calculus people do that work, and then we say, can you write that in a table so I can use it? And they're like, sure, man, I can do it. So we're going to now use a table. I'm going to have a table for everybody of all kinds of values. Because right now, all we know, can you guys remind me from -1 to 1? What's that area from -1 to 1?
2.
Oh, shit. What rule can I use? Because it's normally distributed.
6 times.
Empirical, so within 1 is 68%. I like it. Right? So somehow I know that this is an area of 0.68. Because calculus people did their magic, and they figured out that the area is 0.68. I like it. Sorry. So remind me, what area would this be then?
Whatever.
Well, yeah, figure it out. 68% inside, so how much outside?
66.
32, so half of 32 is 16. Now, does that make sense? That's a small little piece, so that makes sense. Okay, I like it, maybe. Stay with me now. Jeff, he's better than Tylenol PM. All right. If only I could bore myself, I could sleep better. All right. That's right, I'm all done with you. So, what I want to do, let's try to make this transition. I want to get used to this chart. We're going to redo something we did yesterday a little bit, but I really want to reinforce this, especially when you have your own chart to look at. So I'm going to give you guys a one of these. Let me make this really clear right now before I give it to you. Don't write anything on these because you're going to bring them with you to tests. You're going to turn them in with your test, and then I'm going to give them back to you so you can use it for the next test. So you guys with me? If there's any notes on here, that's bad. Okay, it's my effort.
Sure. You want to put our names on it?
Oh yeah, names are fun.
Okay.
I'm just talking about notes, helpful tips that I didn't say you can have. Okay. So the first thing I want to do is really make sure everybody can read this correctly. We talked about this chart a little bit last time. So the way this chart works, so that's what we're looking at, see there? Is if I want to know the probability that, let's just figure something out that we should already know. In fact, what we just now did. So if I had a situation, a normal curve, and I wanted to know what's the area, which is the probability below -1. So to write that in symbols, it would be the probability that the z is less than -1. So these are, why is that 0 there? Because this represents the, what would this represent? Right in the middle. The mean. And why is it 0? Because the z-score is the number of standard deviations away from the mean. So the mean will always become 0 for a z-score. So let's remember this. All right, we're going to use that formula here very soon. So if they give me z-scores, I can just look them up. Because what is this thing? This is a z-score chart. So I have to know the z-score to be able to use this chart. So if I want to know the area below a z-score of -1, I would just look up -1. This is what we did last time, I think. -1.00. So this is how you use it. If I wanted -1.07, I would go -1.07. I would go there. Boop. But I want -1 exactly. So -1 exactly is -1.00. So this top row is the second decimal place. This goes out to the first decimal place. I like it. That's how you read this. Let me stop there. Does anybody have any questions on how to read this? Because if you can't read this, well, you can't do a damn thing. So does everybody see how to read this? Alright. So what's the probability z is less than -1? 0.1587. So this is what we did last time. And we already knew from just what we did earlier that it should be 16%. There's 68% inside. There must be 32%. So 16% on either side. And this is freaking 16%.
Yeah.
Alright, I like it. I like it. So the thing is, I don't know if you guys realize, empirical rule is great, but it's not anywhere near sufficient. Because my z-score, is it always going to be a nice whole number or a nice integer? No, I could get a z-score of 1.48. And then empirical rule is like, oh, I don't know. Okay, so let's try something out here. First off, let me just make sure you guys can read this chart correctly. So, looking at the chart, can you figure out what the probability that z is less than 1.29? Is that a negative or a positive z-score? So you want to look at the positive side. Like, and always draw a picture for yourself. You got to trust me on that. The people that don't draw a picture are the people who are going to make the simple mistakes. If you draw a picture, you can see if it makes sense. So I know this is going to be more than what? What's below 0? 0 cuts it in half, so there should be 50%. So this should be more than 50%. So you know what to expect. So sure, yeah, what do you guys say when you look at 1.29?
0.9015.
What happened?
You were
You're
on
one.
your finger covering it.
1.2.
Yeah.
Why? There it is. Thank you. 0.9015, yes. Thank you. So 90% chance that z-score would be below 1.29. Cool. All right, try this one. That's number 1. Number 2, what's the probability that z is more than negative 2.11? So what area am I asking for? Where would I shade on this picture?
To the right.
To the right. I like it. Because it's greater than. So I know it's going to be more than 50%. It's a really crude way, but at least I can catch a mistake real quick. So if I write down, what did I say, negative 2.11. So if I write down 0.0174, I know I'm wrong. There's no way that big old area is freaking 1%. There's no way. Where is 0.0174?
The left side.
Yeah, good. So the minute you find something in the chart, you put it where it belongs. Now how do I get what I want? 1 minus this, because the whole thing's 1. So that side's 0.0174, the other side must be 1 minus that. How are we doing so far? A lot of the math we've done before this has gotten us ready for this, right? So 1 minus 0.0174, using Jeff's trick, 9826. Now, real quick, do me a favor. Look up positive 2.11. Holy shit, what the hell? Why does that make sense? The amount that's above negative 2.11 should be equal to the amount that's below positive 2.11 because the whole thing is symmetric. There's a shortcut in there. All right, so it's sort of like your car blinkers. If you get the shortcut, use it. If you don't quite, don't. Just do what we just did now. You with me? Because people will do the shortcut and then they'll do 1 minus. I'm like, oh, crap. All right. The blinkers thing is, if you only use it sometimes, don't ever use it, because then you keep the damn thing on, you go the other way, freak me out. Old man Jeff, get all angry. Your blinker says that way, you went that way. Alright, so let's do this. Let's add one more level onto this. So if they give you the question in terms of z-scores, I can immediately go to the chart, because this is the z-score chart. So what do I have to do here? Let's go back to heights, because heights are something that we know is normally distributed. So the heights of men. Sounds like a really boring movie. The heights of men. We know that average is 69. The standard deviation is 2.8. Well, yeah, we'll use 2.8 this time. And I want to know the probability that I get a dude who is taller than 71.5 inches. I'm going to stop right there. So sometimes I give you the question symbolically, and sometimes I just say it in English. So if I said the probability some dude I pick is taller than 71.5 inches, this is what it would look like symbolically, right? Is that cool? Because the variable would be his height. I don't know what it could be, a lot of different things. I want to probably is more than that. So what do I have to do first? Before I can use this chart?
Draw it. Find your z-score. Z-score.
Drawing it, I like drawing it, and finding the z-score. Cool, those two things. So I can draw this immediately. Immediately I can draw this situation. And real quick, I said this out loud, but I gotta tell you it's normal. If I don't tell you it's normal, or if I don't give you a way to figure out that it is normal, you can't use this chart. This chart, because where does this chart come from? It's like empirical rule on steroids, right? Empirical rule only works for normal distributions. So if you don't know and you can't tell that something's normal, you cannot use this chart. You guys with me? Because this chart exists only for normal distributions. So what goes in the middle?
69.
I love it. 69. Now watch this. I really want to force you guys to do what's going to be best for you. Below this, I'm going to put the z-score. What's the z-score for the mean always? 0. Because how far away is the mean from the mean? 0. It is the mean. All right. Now where's 71.5?
Or within.
No. Just where is it?
Just outside.
That way. All right. You gotta listen to me now. Some of you guys might not believe this, but I have people that don't understand that you can't just put it anywhere. 71.5 is freaking there. You can't put it over there. This is a number line like always. If you put it in the wrong place, you're screwing yourself over. Right? The picture is supposed to help you. All right. So it definitely is there. And then to figure out what goes here, I have to do like somebody said. I have to find the z-score. How do I do that?
X minus
Yeah, x minus the mean.
over the standard deviation.
What is standard? So z equals. Careful. What's 69? 69 is the mean. So in this problem, 69 would always come second because it's the mean. X is the data point I'm interested in. Yeah, so 71.5 minus 69 divided by 2.8. 1.12? Is that what somebody else got? Everybody? Anybody who's doing it? I like you guys. You're like, he already did it. What do you want?
I got 0.89.
Uh-oh, 0.89. So let's see. It looks like it's 2.5. Yeah, it should be less than 1. That makes sense. So 0.89? Yeah, 2.5 divided by 2.8. Cool. Should be less than 1. I like it. And now that one step, now I can do just like we did before. Now, which way am I going to shade? It's greater than, so I'm going to shade that way. And again, just like all of that is an arrow pointing you in the direction to shade. I don't know if you remember that from inequality drawing, right? That's nice. If you got your little alligators or whatever the hell, come up here. Right? But that way is the shade. So when I look up 0.89, I'm going to get this area. So what do we get when we look up 0.89? Make sure I get this thing at least once. 0.89. I get 0.8133. Cool. I don't know if I can trust myself. And that's not the answer. That's the answer.
6.1867.
Yeah, so 1 minus 0.8133, 0.1867. I like it. And again, some of you guys might understand the shortcut. If you look up negative 0.89, you would have gotten there immediately. If you don't quite understand the shortcut, you don't have to. Just never try to use it. All right, how do we feel about this so far? I mean, this is almost, how do I say it? Almost too easy on one level to believe that. But if I know it's normally distributed, if I know something is normally distributed, I know a lot. That's why this is relatively easy. That's why in a lot of statistics it's all about tests for normality. Is it normal enough for me to do this? Because then it's easy. If it isn't normal enough, shit, I got some weird ass other things I got to do. Right? So we're always saying, how can I tell if something's normal? Does that make sense? Because if it's normal, I got all these answers just waiting for me to look them up. Right? So what about one last example here? Or two last examples. in the same setup, what if I ask you this question instead? What's the probability that some dude is somewhere between 64 and 68.1 inches tall? Figure that